That's one too. So hello everybody, my name is Jonas Brusakas. I'm currently a PhD student at the University of Aalborg, and I will briefly present our paper on device-independent metrics for measuring energy flexibility. This paper has been co-authored by my wonderful colleagues Fabio and Torben. And I will not really go deep into the details of what flexibility is. We had a very nice presentation beforehand, but unlike our colleagues, who try to measure flexibility generally, we're going to try to measure flexibility for a specific type of flexibility model called flex offers. So flex offers are one of the industry standards of flexibility modeling these days. They offer a unified format to model flexibility from different types of devices. They are exceptionally powerful due to their ability to scale with a large number of devices. They have been effectively almost tailor-made for the aggregation use case, and they capture most of available flexibility with a small trade-off in accuracy. And while preparing and doing this paper, we've observed that a priori measurement of flexibility has been mostly unexplored. Our colleagues have done a fantastic job to actually broaden the state of the art, and you should definitely check out their paper. And the purpose of our work was specifically to analyze, okay, so what is available in terms of a priori flexibility measurement, and how can we improve on that? The state of the art is as follows. So most flexibility metrics are a posteriori. So basically, after you have utilized flexibility, after you have scheduled specific schedules, use cases, after you have received perhaps some remuneration, then most people sort of calculate what is the utility of flexibility. But the a priori measurement of flexibility, having some sort of metric of, okay, we have a flex offer, we have some flexibility, how could that map to some sort of potential utility, has been mostly unexplored. There have been some explicit metrics, specifically for flex offers previously developed, but they have some key limitations and shortcomings, which we will quickly go through. But before we go anywhere, we need to understand what a flex offer is, just for those who don't know. Flex offers have a very complicated looking life cycle, but effectively the typical use case for a flex offer is there are many prosumers having many different types of devices. They want to sell their devices or utilize their device flexibility. They generate flex offers for those devices that model what flexibility those devices have, send those flex offers to an aggregator, then aggregates them into a bigger flex offer, and then uses that flexibility to trade in markets and get some sort of utility out of it. A flex offer in and of itself is actually quite not very complicated, although there are a few types that are a bit more advanced. So here in this presentation, we'll have a sort of running example where we have a smart home battery that can charge at any given time for 7 kilowatts. And in this case, we will assume that the battery can only be charged and not discharged. Flex offers support both production and consumption modeling, of course. And here in this case, the battery, it is visualized that the battery is connected from 1800 up to 700, and then between the hours of 20:00 and 4 a.m., you can charge it anywhere between 0 and 7 kilowatt hours for the given hour. So this is the sort of, and then, the time flexibility here is that we can take this load profile and make it earlier by a few hours, as long as it's not earlier than 1800, and we can consume power at the latest at 700. So there are many types of flex offers that have been developed over the years. This this model has been developed for, I think at this point, over 7 years. So we went through many iterations. What you just seen is known as a standard flex offer. This is the most basic flex offer that we have and that we use. A very natural progression of that historically was a total energy constraint flex offer, which is the same thing, but we also add a total energy constraint, meaning how much energy can be consumed overall within a flex offer. It is very useful for use cases, for many use cases, but most recently, and probably one of the most useful types of flex offers introduced is what's known as a dependency flex offer, which is a flex offer that allows you to model flexibility conditioned on what was consumed or produced beforehand. So you can basically through time say, okay, if I've consumed on the x-axis this amount of energy, then I can consume up to this amount of energy. If I've consumed, for example, at the last time step, if I've already consumed 15 kilowatt hours, which is this toy examples, maximum capacity, then I can no longer consume any more energy. And this type of flex offer is very, very useful in modeling smart batteries. And most recently, it's been used to represent heat energy and conversion between heat energy and electricity energy. So now that we know what sort of flex offers are out there, so what flexibility metrics are available? What is known in the state of the art? There are actually quite a few. I'm not going to go into too many details. This paper does deal with a lot of formalisms. I'm just going to try to give you the motivation and the intuition behind it. There are a few metrics that are what we call atomic. There's time and energy flexibility, which are just basically numeric representations of the sum of all of the energy flexibilities here, taking the minimum possible consumption and the maximum possible consumption and then summing them together. There's also time flexibility, which basically just counts how many time steps backwards and forwards can we push the load profile. There are metrics that combine both, being the product flexibility, vector flexibility. They have their own limitations. Product flexibility, for example, if one of the flexibilities is zero, the entire metric is zero, which is undesirable in most cases. Vector flexibility, try to rectify that by using a vector norm to sort of combine the two. But then the problem becomes that time flexibility and energy flexibility sort of operate on different scales. And very quickly, if you, for example, try to directly optimize on that, you will see that there will be a huge preference for energy flexibility because, of course, there's usually much more of it in terms of that metric. There are a few other metrics that have been introduced to sort of try to rectify and model flexibility. There's time series flexibility, which introduces the notion of a minimum and a maximum schedule. So basically two possible extremes. A minimum schedule is the earliest possible schedule with the least amount of energy consumed. The maximum schedule is the polar opposite, is the latest possible schedule with the maximum amount of energy consumed. And then we take a vector norm between the two. This has a very intuitive problem that it's not very easy to compare. So two flex offers calculated by the flexibility is calculated by the time series flexibility because they're not really consistent. Assignment flexibility tries another approach. They try to discretize flex offers into basically integer energy values and then combinatorically count how many types of schedules can you actually dispatch. It has different problems, mostly due to the fact that discretization is lossy and you actually start losing out on details and makes it also quite difficult to compare. There's also the area-based approaches, which takes us the maximum and the minimum schedules and then computes the area between them. They also have similar problems. So the first step that we did in this study, after analyzing what exists, is we noticed that actually all of these metrics were defined only for the standard flex offer. They were defined very early in the flex offer lifecycle, in the development of the flex offers. So the first thing that we did was actually extend all of these metrics to support total energy constraint flex offers and, most importantly, dependency flex offers. I don't want to go into too many details of how we did that because it's quite a formal thing, but the intuition is quite simple. We just calculate the area, the total possible area of the flex offers and the dependency flex offer and all their slices, and we just adapt that to the metrics, which for most metrics is actually quite easy to do using the notions of average energy. However, one metric stood out slightly, and that was the assignment flexibility. That is the one that discretizes the space. So we had to write an algorithm that looks quite complicated, but actually isn't. We literally go through each step of a dependency flex offer and then calculate how many schedules can we dispatch for each step and then sum them together. And that's your assignment flexibility. We noticed while extending these metrics that actually these extensions didn't solve any of the problems that these metrics have. So the same limitations that they had before, they have now. And this gave us some motivation of trying to create a few more metrics to see perhaps if we could at least propose a potential solution of how we could solve some of the limitations. So there are two a priori metrics that we have defined in this paper. They're both effectively generalizations of existing metrics. Advanced vector metric is basically a generalized vector metric. One of the biggest problems with it is the fact that the time flexibility sort of operates on a different scale to energy flexibility. So we just try to introduce a coefficient alpha that allows us to select how much weight do you put on time flexibility and try to sort of normalize it manually. There's also advanced assignment flexibility. We try to solve the problem of the assignment metric that normally the assignment metric only operates using integer values for energy, and that of course can be lossy, especially if you have floating points, which often you do. So the assignment metric basically allows you to reduce the discretization interval and basically create discretize with a smaller step size, which increases the accuracy of the metric with a very small trade-off of longer runtime, which is insignificant, to be honest. But another metric that we introduced is actually an economic metric. This is actually an a posteriori metric. This is akin to what we call utility. This is basically, it measures the cost obtained by finding an optimal schedule in terms of cost for a given flex offer. And this is basically, this is you can think about a minimum price that you would have to pay for executing the optimal schedule for a given flex offer. So basically, for example, to charge your battery up to a desired level. This is a meaty slide. We try to formalize mathematically what a flex offer metric should have, what type of properties it should contain, such that a metric could be used for almost any use case that we're using flex offers for. The math here is, if you don't like notation, don't look at it. Actually, it is quite intuitive. Generality basically means that it is defined for all types of flex offers. Positive definitiveness means that a metric should give a 0 value to flex offers that represent no flexibility. So if only one schedule is available, if there's only one type of execution available from a flex offer, it should have a value of 0. Monotonicity and consistency and aggregation deal with comparing flex offers in and of themselves. So if we have, for example, in terms of monotonicity, if we have a flex offer G that is a subset of flex offer F, then you would want the metric value of F to be greater or equal to G's. And there's also a strict version of that if one is a strict subset, then it should have a greater value specifically. We basically extend monotonicity to aggregation, which is a very common use case for flex offers. And then another metric property, which is quite important, is translation invariance. And that basically means that if you take a flex offer and you push it forward or backward in time, basically push the same amount for the start time and the end time and on all the energy profiles, that should not change the value of the metric, because actually the amount of flexibility is still the same. It's just that you can activate it slightly earlier or later. So we compared all these metrics, first of all, in a qualitative analysis with regards to the properties that we defined. A few key points. Now that we've extended all of these metrics, they all comply with generality, which is great, because we do want to be able to measure all types of flex offers. All the metrics more or less comply with the monotonicity, meaning that you can compare them quite nicely. For product and time series, these are non-strict monotonicities. For assignment metrics, it's a little bit complicated because there is a little bit of lossiness that is introduced by discretizing, so they're not exactly comparable. But a key takeaway is that for the vector and the advanced vector metrics, they comply with all of the properties. So now actually in current and future studies, we are going to just use the vector metric as a sort of default catch-all case. And we're going to recommend it to the people in industry to use it, because it doesn't really have any clear limitations, apart from the fact that, of course, you need to scale your time flexibility slightly. Simulations. We also wanted to do some quantitative analysis, try to see, okay, so do these metrics actually map or correlate with some sort of notion of utility? And we came up with an experiment where basically we generate, we simulate 256 heat pumps and EVs, and then we perform cost minimization, trying to find the cost optimal profiles for execution for flex offers generated on top of these devices. And then we evaluated, okay, so how much would it actually cost, let's say in the year 2018, based on spot and imbalance prices, to actually charge these batteries or operate these heat pumps? And then we correlated that with the metric values calculated for the flex offers from these devices. And of course, we calculated those values and then tried to correlate them using Pearson and Spearman coefficients for two use cases. The first use case is what? The first use case was correlating the metric values to the cost minimization case, where we're trying to find the minimum case, the minimum cost case, the metrics don't correlate at all well. At best case, we can call it a very weak correlation. I would actually say that this is no correlation, but it's the eye, beauty is in the eye of the beholder. You could say that the vector metric out of all of them exhibits something that is almost considered a weak positive correlation, but that's again debatable. But this is actually quite intuitively explainable. The prices in the imbalance market, spot prices that we had, they fluctuated a lot, and these metrics have no information about what the market was operating at and what sort of prices were available on the market. However, we also introduced another experiment, which was taking the difference between the maximum cost and the minimum cost, which we sort of intuitively call the risk, which is sort of gives you a range of how much cost difference can there be between the optimal and the most suboptimal case. And then we correlated that to metrics, and that actually correlates quite nicely. The upshot is that actually for most metrics, apart from the assignment that has a bit of a problem because of the discretization, they have a positive correlation, with the metric vector metric having a fairly decent linear correlation with a Spearman coefficient of 0.98, which means that at least for this case, it's a decent estimator. Key conclusions. The metrics that we have just seen are quite okay and quite decent at estimating the price difference of so-called risk, especially when there's no time flexibility. Time flexibility is a little bit of an issue generally. A priori metrics are not magic. They cannot estimate the economic metric without accurate energy forecasts. If we had to recommend a metric to use for flex offers generally, we would recommend the vector and advanced vector metrics, because they have all of the desirable properties, especially in cases of aggregation, and they're quite decent at estimating or at least being somewhat correlated to the two use cases that we've shown. And in future work, we will try our best to extend these metrics to one more flex offer type, which actually captures uncertainty in terms of production and consumption, and also try to figure out if there is a reasonable way of how to better perhaps estimate utility in terms of price, maybe by informing the metrics about statistics about what the markets usually clear at and what are the historical prices in the markets that we're trying to trade. But that is pretty much that. We wanted to give many thanks to the European Horizon 2020 projects that co-funded this research, and I will have your questions. Thank you.